Hey guys, so today we're going to be learning about physics, but of course, more importantly, states of matter. So we have already looked at the law of conservation of solids, so what about liquids? Pressure is a type of conservation of fluids. Pressure is the force over surface, so that's why we define it as force over area. Pascal is a unit of measurement that is used to describe pressure. It is very, very tiny. And no, I'm not talking about the chameleon from Tangled. I wish. Anyway, pressure is all about where you are. If you were standing on the moon, pressure is much different than if you were on Earth. There is also pressure caused by gas particles that bounce around and make all these little tiny elastic collisions. This happens in almost everything due to atmospheric pressure. Atmospheric pressure is also always present on everything at sea level on Earth. The force of atmospheric gas is about 10 newtons. There is also a table from the book that shows other locations and the pressure that is there. So now we can put this in an equation. So let's say you have a table that's 4 meters squared and you set something on top of it that's 10 newtons. If P equals F over A, then P must equal 10 over 4 meters squared. So if you do the calculations on that, then you get 2.5 pascals. Don't forget the unit. Next, we have different gas laws. The combined gas law discusses how pressure relates to temperature, volume, and the amount of gas. The equation explicitly shows the relation and how one is equal to the other. P1 times V1 over T1 equals P2 times V2 over T2, which is ultimately equal to a constant. The ideal gas law talks about how kinetic molecular laws relate to the combined gas law. Pressure times volume divided by temperature ultimately gives you a constant called Boltzmann's constant times the number of particles. So, moving on to 13.2, we're going to be talking about forces within liquids. First, we have adhesive forces, which is when fluid wants to cling to outside forces. As shown here, we have water that tends to cling to the sides of glass, creating a little dip. Next, we have cohesive forces, which is when water is attracted to each other and they want to cling to each other, such as surface tension, when you touch the surface of water and it wants to stay together and not let your finger break through the water. The next term we have is viscosity. Viscosity is the internal friction of fluids, which is basically how thick a fluid is. So oil has a greater viscosity than water does. Next, we're going to talk about evaporation, which is when water is heated up so much that the fast-moving particles break and then go into the air. There's also condensation, which is basically the opposite of that, when the air particles start moving so slowly that they begin to pool and they can turn into a fluid. This is most commonly seen in places where there is high humidity, and in the mornings there will be dew on the grass or on the leaves on the trees. Finally, we have evaporative cooling, which is basically just a function of evaporation. And it's basically the idea that there's a cooling effect when fluid is evaporated. So that's why when humans sweat, they release fluid from their skin, and when the fluid is evaporated, it leaves the skin feeling cooler. And that's a way that we can cool down our bodies for survival. So the next section is 13.3, fluids at rest and in motion. So now that we are done with the last section, we are going to take all the terminology that we learned and apply it. First and foremost, there is a lot of pressure underwater. The deeper you go, the more pressure there is on your body. Pascal created a theory that if there was a change in pressure anywhere in the fluid, the change would be felt undiminished throughout. There is an equation that represents the force exerted by a hydraulic lift, which is the force exerted by the second piston being set equal to the force of the first piston times the area of the second over the area of the first. The pressure of water on your body is as follows. Pressure is equal to the density of water times the height of the column of water on you times the acceleration due to gravity, which we all know is negative 9.81. There's also a huge contributing factor called buoyancy. This is a very big topic when discussing force underwater. Buoyant force is equal to the density of a fluid times the object's volume times the acceleration due to gravity, which is negative 9.81. In a real-life example, this is a glass of water with a metal straw in it. The straw goes completely through the water because metal is heavier than the water. Therefore, its buoyancy is very, very low, and it will sink. Now I have put this cap in the water, and it floats perfectly. Even if we take the straw out, the cap still floats. We can move around the water, and the cap still floats. This is an example of buoyancy. The cap has higher buoyancy than the straw does. Next, we have section 13.4, which is all about solids and how solids differ from liquids. There are properties to freezing liquids. Solids become more dense, except water. Water is the most dense at 4 degrees Celsius. Another factor is elasticity. When solids are manipulated, they have a tendency to go back to their original shape, and that all depends on how elastic they are. Malleability and ductility are also elastic properties. As solids are heated, they expand, and to describe this, there are 2 different equations. The first of these equations is the coefficient of linear expansion equation. This equation describes that the change in length over the original length times the change in temperature will give you the coefficient of the linear expansion of that material. The other equation to talk about expansion is the coefficient of volume expansion equation. This is basically the same equation as the linear expansion equation, except for we're talking about volume instead of length. So the coefficient is the change in volume over the original volume times the change in temperature. And this is a table from our book that has some common coefficients of thermal expansion. Knowing the different applications for thermal expansion can be really useful, mainly in certain construction or architecture jobs in which you need to know the expansion of metal when you heat it up or different materials like that. And that's the end of the chapter. Thank you guys so much. I learned a lot, and I'm so happy that I could share what I know with you guys. Bye, Doc.